like, share, subscribe.
Hey y'all, welcome back. Today we're going to learn how to solve polynomial inequalities. So these are going to be a little different than solving a polynomial equation in that instead of having an equal sign, these will have less than or greater than, or even on a rare occasion, a not equals to symbol. Now to solve these polynomial inequalities, we're going to use one special fact to help us find the solution sets, and that is that a polynomial can only change sign, like go from negative to positive or positive to negative, at the zeros. So the strategy is typically going to be, we're going to find the zeros of the function, usually by factoring, and then examine the intervals in between and outside of those zeros to figure out whether or not the function is positive or negative. And once we find the sign of the function for all of its defined x values, we can state whether or not certain x values are in the solution. So to kind of walk you through this, the first thing, like I said, is we're going to find all the real zeros of the polynomial. Now, what we do after that is we're going to draw like a number line, and we're going to place all the zeros that we found on that number line. Once we do that, we'll see that the number line has been sort of divvied up into these different intervals in between each of the zeros and even on the outsides of the most extreme zeros. For each interval, we're going to pick one representative, sort of represent that entire interval, plug that into the polynomial and find out whether or not the function is positive or negative. Now, you might be thinking, okay, well, picking one representative is not enough, but then I want to go back to the notion that the sign of a polynomial function can only change at the zeros. So in any of these intervals in between the zeros, the function will be completely positive or completely negative for the entire interval. Now, I think this will make a lot more sense as we work through a problem. So I think, if we just jump straight into the to the examples here, what I'm saying will hopefully make a little bit more sense. So here's an inequality, and like I said, what we're talking about when we're talking about inequality is these when you have something like less than or greater than rather than an equal symbol. So the first step is going to be to find the zeros of the inequality. And what I mean by that is we want to set this polynomial function equal to 0, and then find the x values that satisfy that equation. So out to the side, maybe I'll make a little note here. Number 1, step 1, find the zeros, okay, or find the x-intercepts. Okay, so I'm going to set up an equation, x squared. Let's make this a little bigger so you can see it. Minus 2x minus 3 equals 0. Now, we can factor this. This is factorable as x minus 3 times x plus 1. And then we can use the zero product property to set each one of these factors equal to 0, and we'll solve them individually. This particular polynomial is quadratic, right? The degree is 2, so we're expecting 2 roots, and we do get 2 roots. We get x equals 3 and x equals negative 1. Okay, so once you find the zeros, we know that the sign of this polynomial can only change at these zeros. In other words, like all the values of the function are going to be all positive or all negative in between these two numbers. So the next step after you find the x-intercept, so step 2 here, is going to be to create a number line. Okay, so draw a number line with the zeros labeled. Okay, so draw a number line with the zeros labeled. So I'm just going to really just sketch one out here. And it doesn't have to be to scale or anything. Just get the negative 1 and 3 on there. So what we can see here is we've sort of divvied this up into 3 intervals. There's this first interval, which goes all the way to negative infinity. And then the second interval is in between -1 and 3. And then the third interval goes from 3 all the way to infinity. Now, since the sign of the polynomial can only change at these zeros, inside this interval it's going to be completely positive or completely negative. So for each interval we have here, we're going to choose a representative to establish whether or not the function is positive or negative in that interval. So step 3 is going to be to choose a representative from each interval to test for, I'll say test for the sign of the function in that interval. Okay, so basically we need to pick a number, and it doesn't really matter which one, so you want to pick numbers that are easy to calculate, and we're going to plug it into the original function. It could be like the original one up here, or it can be the factored version, whichever is easier, and find out whether or not the function is positive or negative, and we'll make a little note on the number line. Okay, so let's say, let's pick a number less than -1. I'll say -10. But again, like, it doesn't really matter what the number is as long as it's in this interval. So here, I'm going to pick -10. In between -1 and 3, I'm going to pick 0. And then after 3, I guess I'll just pick 10. Okay, something that is going to be as easy as possible to calculate. So I don't need to know the number exactly, what I get when I plug these in. I just care whether or not it's positive or negative. So for example, if I plug in -10, this factor would be negative, and this factor would be negative. And a negative times a negative is a positive. So what we know is that in this interval, the function itself is completely positive. Okay. From -1 to 3, my representative is 0. So if I plug in 0, I get a negative times a positive. A negative times a positive is negative. And then if I plug in 10 here, I get a positive times a positive, which is positive. So between -infinity and -1, the function is above the x-axis. Between these two values, it's below the x-axis. And above 3, it'll be above the x-axis. So if the question is, when is this polynomial less than 0? Okay, so we want to know, when is the polynomial less than 0? It's going to be less than 0 between -1 and 3. So my last step, step 4, is going to be to really just write the answer. So write the solution set, and I'm going to suggest you use interval notation here rather than inequality notation, although if you do write it using inequality notation, that's fine too. So the way we're going to write this is we're going to say x is an element of, so let me actually grab that symbol. I don't think Cami has it. Oh, maybe I don't have it either. Let's double check here. Does Cami have this symbol? I want to say it doesn't. Yeah, it doesn't. Okay, so I'm just going to have to draw that in. So we're going to use like this symbol right here. It almost looks like a C with a little line through it, almost like an E, but it's like if C and E had a baby. That's what it would look like. And what this symbol means is it's an element of. Okay, and then we'll just list the set. Okay, the function, the polynomial is going to be negative in between -1 and 3. So I'm going to say parentheses -1, comma 3. And that, all the values in here will be solutions to the inequality. Now, if you understood our last lesson where we were sketching out polynomial functions, you can kind of do this a little faster, actually without using representatives. Like if I just do a quick sketch of this, right, and I say, okay, I still have to find my zeros, you can't really get around that, but if I understand what the end behavior is, right? Like if I say, okay, well, this has an even degree and a positive leading coefficient, then I know my end behavior is going to be up, up. Both of these roots are single roots, so I'm just going to pass through, right? So if I do a quick sketch, I can see, pretty quickly that this is going to be negative in between -1 and 3. So this is just an alternate way of solving it. I'm going to use this number line primarily, but I might use the sketch as more of like a checking mechanism, but really either way should work. So let's take a look at another example here. And we'll just kind of work through a few examples, and then we can start working on the homework. Now, when we solve these inequalities, we do need to have the right-hand side be a 0. So in this case, what we would need to do is subtract 7 from both sides, just to kind of get this started. Is greater than or equal to 7. Okay. Not 7, 0, sorry. And then we need to find the zeros. Okay, so I'm going to factor this as the first two terms has got to be 2x and x to get 2x squared, and then my factors of -7 are either 1 and -7 or 7 and -1, and I need the middle term to add up to -13. So I think what I need here is -7 over here plus 1 here. That would be -14 plus 1 would be -13. So these would be my factors. We can see at this point that my two roots here are going to be, and maybe I'll just make a little note here, my x-intercepts are going to be at -1/2 and +7. All right, so I'm going to draw my little number line, and I'm going to place -1/2 and 7 on this number line. And I'm going to pick representatives from each interval to decide if it's positive or negative. Now notice that these are both x-intercept. So like the value here is 0, right, at both of these numbers. So when we go to write our solution set, since we want to know when is it greater or equal to 0, we do want to include these values in our set. So like up here, we did not include -1 and 3 because this said strictly less than. So we don't want to know when it's equal to 0, which would be here and here. We wanted to know when is it going to be negative. Whereas here, we're looking for where it's either going to be positive or 0. So I'm going to pick some representatives here. So I'll just make a little, let's see, my representatives here. Let's say I pick -1, seems good, 0, and 10. Okay, so if I plug in -1, this would be -2 plus 1. That's going to be negative times a negative, so it's going to be the value of the function is going to be positive right here. And then in between here, if I plug in 0, I get a positive times a negative, which is negative. And then if I plug in 10, I get a positive times a positive, which is positive. So I actually have two intervals here that will satisfy it. And so the way we're going to write that is x is an element of, I really wish Cami had a symbol for that. Probably has a way to get it in there. I'll try to look for that later. But anyway, so we've got two intervals here, right? Where this is going to be positive in between -infinity and then -1/2, and then from 7 to +infinity. So the way I'm going to write that is on the infinities, you're always going to have a, does this not have an, oh yeah, it does. You're always going to have a parentheses here because you can't actually get to -infinity. We're just going to approach it. And then to -1/2. Here we will have a bracket though, because we do want to include the -1/2 in the solution set because it can be equal to. So basically, if it could be equal to, you want to include the 0. If it's strictly greater than or less than, you do not include the 0. All right, now the symbol we use to show that we have a union of two sets, or we want to actually say that there are multiple sets where this polynomial is positive, we're going to use this U symbol. It stands for union. And then our second set would be from 7, and again, we are including 7 to infinity, and the infinity will have a parenthesis on it. So this would be our solution set for this inequality. Again, we could approach this not using the number line, but if we just sketch, kind of like what we did in the last unit, We still need to find those zeros, so like if we have them at -1/2 and +7, and we note the end behavior of the graph would be up and up because we have a positive leading coefficient and an even degree, then we can see pretty clearly that this function is going to be greater than or equal to 0, or positive essentially, here and here. So there's how you solve that one. I guess the key takeaway here is you want to make sure this thing equals 0 before you start the problem. Let's take a look at a couple more, and then that'll be it for today. So the past couple of examples were quadratics, and this one is a cubic. So you want to be a little careful when factoring cubics. These cubics are going to be set up so that they are going to be factorable in one of two ways. The easier factoring is going to be when you can factor out a greatest common factor, a GCF, and then usually that devolves the factoring into factoring a quadratic. But in an example like this, there's not going to be a greatest common factor here. So the big question is, how do we factor this so that we can actually find the x-intercepts? Now first, you do want it to just have a 0 on the other side, so you want to add 48 on both sides. But then once you do that, we can factor this by grouping. It's just for cubics, the grouping is just a slightly bit different than factoring a quadratic in that you already have your 3 terms, okay? So when you go to factor your GCF, you're going to skip straight to the grouping part of it, meaning like you group your first 2 terms and your last 2 terms, you factor out your GCF, and then from there it's the same as grouping a quadratic. So if I look at the first 2 terms, you might notice that your GCF is going to be x squared. So I'm going to say x squared times 2x minus 1. And then the GCF for the second one is going to be 16, or -16. So I can factor out a -16 and be left with 2x minus 1. Now, if this thing is actually factorable, which they should be set up so that they are factorable, you're doing it correctly if what's inside the parentheses is the same binomial. So notice we get 2x minus 1. If these two are different, then you need to go back and try again. Or it is possible that you have a GCF that you can factor out. So you want to first look for a GCF. This one doesn't have a GCF, so we're just going to start the grouping process. And we do get the same thing in both sets of parentheses here, so that indicates that we're on the right track. From here, our 2 factors are going to be 2x minus 1 and x squared minus 16, which is factorable, but you don't really have to factor it because you can solve it like almost linearly. Basically, you would solve it using square roots by adding 16 and then taking the square root. So once it's all said and done, we get our x-intercepts at 1/2. And then let's see, if we add 16 and then take the square root of both of 16, we're going to get plus or minus 4. So we're going to get -4 and 4. So we get 3 x-intercepts. These are going to be the numbers that we plot on the line. So let me draw my little number line here. We've got -4, 4, and 1/2. And now let's pick some representatives. So I think what I'm going to do is, let's see, let's just make a little note of what I'm picking here. So my representatives just need to be any number in these, looks like we have 4 intervals here. So I'll pick -10, 0, and 10. You know, you might notice I'm usually going to pick like the same kinds of numbers every time. Because really I just want this to be quick and easy, right? Like I want to be able to plug this in and just know really quickly if this is going to be positive or negative. So if I plug in -10, I'm going to get a negative times a positive. So this interval should be negative. Just going to make a little note that this is negative. Now if I plug in 0, then this would be 0 minus 1, that would be negative, and a negative times a negative is positive. If I plug in, I get a positive times a negative, so that would be negative. And if I plug in 10, I'd get a positive times a positive, which is positive. So we can see the signs real quick, and now we know when this is greater than 0. In other words, when is it positive? So my solution set is going to be x, and we're going to write is an element of and we'll include both sets where it's positive. So we're going to use parentheses here because we are dealing with an exclusive situation where the endpoints are not included. It doesn't say greater than or equal to 0, it just says strictly greater than 0. So between -4 and ½ would be the first interval, and then the second interval would be in between 4 and infinity. And yeah, so that would be a solution set. Just to kind of stay consistent here with the sketches, you could have sketched this out once you find the x-intercepts at -4, ½ and 4. We can look at the leading term, which is 2x cubed. That's got a positive leading coefficient and an odd degree. So the function will be going down to the left and up to the right. There's no multiplicity on any of those roots, so we're just going to pass through each x-intercept. And so we can get an idea of what the graph looks like. And this does match up with our conclusions here with the signs of the function, right? It's negative, positive, negative, positive. All right, let's do one last one here. Now, this one is not factorable. So what's going on here? Is this one even solvable? Let's see. If it's not factorable, we got to go back to the good old quadratic formula. So we get x equals -b plus or minus the square root. Where's my square root button? Square root of b squared minus 4ac divided by 2a. And I think I see what's going to happen here. Maybe you do too. We've got -2 plus or minus. I'm just going to simplify this before we go too far. Plus or minus the square root. We've got 4. Oops. Minus 16, which is going to be -12. So you might be saying, okay, wait a minute, what's going on here? But what this means there's no real solution here, right? So what that means, as far as we're concerned, is that there are no x-intercepts, Now, that might seem like a problem, but really all that means is that the sign will never change because this thing's never actually touching the x-axis. If it's never going to touch the x-axis, it can't change from positive to negative or vice versa. So the entire function, which, since this is a quadratic, will look like a parabola, is either going to be completely above the x-axis or completely below it. So what we are going to have is a number line here with no key numbers. It's just going to be one interval. So it's either, like, our answer is either going to be all real numbers or no real numbers. We want to know, when is it greater than 0? So we want to know, like, is this positive or not? There's no x-intercepts here, so we don't need to label anything. We will pick a representative, but this representative can be any number you want, since there's just one big interval. So the representative I'm going to choose here is going to be 0. I always pick like the easiest number to compute mentally. 0 is pretty easy. 0 squared is 0, 2 times x is 0, 0 plus 4 is 4. So that means on this interval, the whole function is going to be positive. Okay, in other words, I might not know exactly what the graph looks like here, especially because I don't really have, the only thing I really can quickly find without like making a table or anything is this y-intercept of 4, right? But this thing is never going to cross the x-axis, right? So it's probably going to do something like this, okay? And to get more information, really at this point, we would need to create a table. Later, when you get to calculus, you'll figure out how to find these relative extrema. And so you can improve the accuracy of your graph that way, but I'm not going to expect you to know how to do that in precalculus. So The answer to this question, though, is that this function is always greater than 0. So the way we would write that is that x is an element of the set. I mean, you can just say all real numbers, but if we're going to use interval notation to write all of our solutions, let's just stick with that. And so we'll say x is an element of the set, negative infinity to infinity. So this is kind of a special case where you don't get any x-intercepts, but I just wanted to show you one where that could potentially happen. So I think that's about it for today. We're really just focusing on these polynomial inequalities and learning how to solve them. Next time we'll look at some more complicated inequalities, and in particular rational inequalities. Y'all have a great day. Let me know if you have any questions, and I'll see you next time.